Hello. Today we're going to continue Chapter 7, looking at Section 2. So we've already talked about Kepler's 3 laws and the law of universal gravitation, and now we're going to apply that law to things like planets and satellites. So let's talk about satellites first. When Newton imagined satellites, he imagined a cannon firing objects at a very high velocity from a very high point so that they would then enter Earth's orbit and orbit around Earth. And so he imagined that they would fall toward Earth at the same rate that Earth's surface curves away. And so we would say that that means that those objects are in orbit. So basically, if they keep falling toward Earth at the rate the Earth's surface curves, they're just going to keep following that orbit of Earth. And so there is an equation that we can use to calculate the speed of a satellite orbiting Earth. And so we use v to indicate our velocity, and it's the square root of our gravitational constant times the mass of Earth divided by the radius. So the distance between Earth and the orbiting object like a satellite. We can also find the period of a satellite orbiting Earth, or the amount of time that it takes a satellite to make one orbit of Earth, and that equation is capital T is equal to 2 pi times the square root of the radius cubed over the gravitational constant times the mass of Earth. This would also apply to any orbiting object, but specifically we're looking at satellites orbiting Earth. So we can use these equations for any object. The mass of a satellite is going to be limited by the capability of the rocket that we're using to launch it. So if the satellite's really heavy, the rocket has to be able to propel it up high enough in order to enter Earth's orbit. As the distance between Earth's center and the object becomes larger, the acceleration due to gravity becomes smaller. So as we get further away from Earth, our acceleration due to gravity gets smaller. And this is why you feel weightless in space, because everything is accelerating toward Earth together, and so there really aren't any contact forces. So the further away you get from Earth, the more weightless you're going to feel. Another big thing with objects, especially in space, is the gravitational field. So gravity acts between objects that are not touching or close. Gravity acts from a distance, and it's not something we can see, it's more something that we can feel. And so this is what's called a gravitational field. It's a field that surrounds any object with a mass, it's like a magnetic field, and it causes other objects to experience a force due to the interaction between the object's mass and the gravitational field. So when we talked about the universal law of gravitation, we talked about the relationship between mass and the distance between the objects. And that's what we're talking about here. So there is an equation we can use to find the gravitational field, and that is due to the gravitational constant times the mass divided by the radius squared. So how far away are those objects from each other? This gravitational field depends on the mass of the object itself, not the mass of the object it's acting on. So if we're talking about Earth's gravitational field, then this mass would be the mass of Earth. And then our R would be the distance from Earth to whatever object is experiencing the gravitational field of Earth. To find the gravitational field of more than one object, we would just find the gravitational field of each one and then just add them together like vectors. Okay, when we talk about gravitational field, we've talked about how the mass of one object affects the gravitational field on another object. And there are also two kinds of masses. So the first type of mass is an inertial mass. This is the mass that's related to the inertia of an object. And remember, inertia is an object's resistance to change or resistance to any type of force. So the more mass we have in general, the more resistant the object is going to be to this change or an application of a force. We can find the inertial mass by taking the net force divided by the acceleration. And that's just a rearrangement of the force equation. The other kind of mass is gravitational mass. And this determines the size of the gravitational force between the two objects. Remember, we talked about in the universal law of gravitation that if we increase mass, we're increasing the force between the objects. We can find the gravitational mass by taking the radius squared times the force due to gravity divided by the gravitational constant times the mass. And this is the mass of the other object. And so if we're looking for the gravitational mass of Earth, then our R would be the distance between the objects, the force, the gravitational constant, and then M would be the mass of the object that Earth is putting its gravitational force on. Newton came up with what he called the principle of equivalence, where he said that the inertial mass is equal to the gravitational mass in magnitude. And so, for example, let's say that you have a watermelon in your trunk. If you accelerate your vehicle, the watermelon is going to roll backwards. And the reason it's going to roll backwards is due to inertial mass. If you accelerate your vehicle, you're putting a force on that watermelon, and its resistance to that force is inertia, and it's going to accelerate backwards in your trunk. You could also drive your vehicle uphill, and that's also going to cause the watermelon to roll to the back of the trunk, but the reason it's rolling to the back of the trunk this time is because of gravitational mass. And so if you just happen to be driving along and all of a sudden you're going up a hill, now the watermelon will roll backwards due to gravity, not inertia. But if we had these two instances and we calculated the masses, they would be equivalent in magnitude. Well, Einstein really liked this principle of equivalence too, and he used it in his theory of gravity. And he said that gravity is not a force, like Newton proposed, but it's an effect of space itself. He said that mass can cause space to curve, and other bodies will accelerate around this massive object because of the way that they follow the curved space. And so as you can see in this picture up here, we've got Earth, and it's bending space due to its mass. And so then this satellite is orbiting Earth based on that curving of space. And this also led to Einstein's theory of general relativity, which says that explains how massive objects affect one another. And that's due to this bending. If we have really massive objects, we can also bend light. And so this is also what creates a black hole. So in a black hole, the object that creates the black hole is so massive and dense that the light that leaves it gets completely bent back towards the object. And so basically nothing can leave this pull of mass, and we call it a black hole. Einstein's theory, however, does not explain the origin of mass or how it curves space. It just says that it does and how it affects other objects. Okay, so we are going to do this practice in class, but again, please feel free to try it on your own. And then here's the homework, and the answers are also on your outline. Have a good day.